Okay, well, thank you for having me, and thank you everyone for coming. Today, I would like to talk to you about a truly enormous new imaging survey of the sky that astronomers are planning to commence in late 2024, early 2025. The survey, called the Legacy Survey of Space and Time, or LSST, will run for a 10-year period. And this survey is going to be conducted by this observatory shown here, the Verne C. Rubin Observatory, which is located on a mountain in north central Chile. That's where it is on a map of South America. And the observatory is significantly built already. There still is some further work to do, but it's coming along well, as you can see from an image like that. That's from just a couple of months ago. By the people who are building the observatory. The observatory is named after Verne Rubin, shown here. She was an American astronomer who made key contributions to understanding the dynamics of galaxies, as well as the study of dark matter. And this observatory is a large national and international project. By the time it's fully built and then operated for its 10 years, it will be pushing $1 billion in terms of full cost, probably around 800 million or so. This money has been kindly provided by the National Science Foundation and the Department of Energy and private philanthropy and other organizations as well. And as I will say, I think this observatory has enormous potential for scientific discovery, for education, and for citizen science. And I'll try to cover all of those things in this talk at an overview type level. Okay, so what I'm going to do in this talk is I will start with a brief overview of the Rubin Observatory and LSST. I will then talk about some LSST science prospects, and I will end by talking about the education and citizen science opportunities. So let's start with the overview of the Rubin Observatory. So again, here is the picture recently taken of the Rubin Observatory. I want to show you the telescope, which is located down in here. So if you look down in there, a telescope is being built. This is what the telescope looks like down inside that dome. That's the telescope. And here is a zoom in on the telescope. And this is a very large telescope. Just to give you a sense of scale, that's the size of a person there. Okay. This telescope has been built from end to end to be a powerful survey facility. This is a telescope that surveys enormous swaths of the sky. It doesn't pick individual particular objects and focus on them. Its goal is to cover as much sky as possible in a highly efficient survey mode. The telescope is an 8.4 meter diameter telescope. Although due to the technical designs of exactly how the mirrors are made, it effectively operates as a 6.4 meter mean effective aperture. And this is probably the most remarkable thing about the telescope. The telescope has been specifically designed to have an extraordinarily large field of view. The field of view is about 10 square degrees. To give you a sense of what that's like, that's about 50 times the solid angle of the moon up on the sky. So every time this thing points at a patch of the sky and observes, it gets 10 square degrees, 50 times the size of the full moon. And to put that into further perspective, you've seen, of course, all the beautiful images from the Hubble Space Telescope, now the James Webb Space Telescope. This thing's field of view is like 3,000 times that of the Hubble Space Telescope. So that shows you how much of a wider grasp on the sky you get from this facility. To image that much sky effectively, well, you have a very specially designed telescope. It uses 3 reflections off of mirrors and then a set of lenses to give you sharp imaging over that enormous field. And then it requires an enormous camera to gather all the data. The camera is a 3.2 gigapixel camera. Okay, so that's truly enormous. It's 189 ccds. Just the camera alone up in here is almost the size of a car. So the thing is enormous, just the camera. And to give you a sense then, that's comparable to the imaging of 270 iPhones held side by side. And everyone can relate to that, I'm sure. So it's an enormous camera that gathers an enormous amount of data, as I'll be saying. So then, to sort of put LSST into perspective, here it is in terms of mirror size. It's not going to be the biggest observatory ever. That's not its thing. We are currently constructing observatories that will be larger in terms of just light gathering power. However, as I said, these facilities are predominantly focused on highly detailed studies of small fields and individual objects, whereas Rubin is designed end-to-end to be a powerful survey telescope. And that's what makes it unique. And what is Rubin going to do? Well, it's going to conduct, as I said, the legacy survey of space and time. And if you had to say one sentence to describe the legacy survey of space and time, it's going to be an optical and near-infrared survey. Okay, and here, in fact, are the photometric bands. There are 6 photometric bands that Rubin will cover, running all the way from, the very blue, okay, out through the red and near infrared. Okay, these are the 6 photometric bands here. That's their bandpass coverage. It covers 6 bands. And it's going to cover about half the sky, the southern sky, the sky viewable from that location in Chile, to superb sensitivity. And I'll show you more about what I mean by that in a minute, based on about 820 visits over a 10-year period. And that's the other critical point. This facility is not just making a picture of the sky, it's making a time domain movie of the sky in color over that 10-year period. You go to any particular point on the southern sky, there will be a movie made of 820 images, okay, in those different colors that you can use to look at how cosmic objects vary or move over time. So it's a movie of the sky. And so LSST aims to be a wide survey covering, as I said, the entire observable southern sky. It aims to be fast. It's going to rapidly scan the sky. And the individual observations with Rubin are going to be short. They're going to be like 15-second snaps. And they'll do 2 of those back to back to make a 30-second snap. And by doing that repeatedly, you can cover the whole observable sky every 3 to 4 nights, okay? And that's what allows you to build up this color movie of objects that change or move. And then in terms of deep, in terms of the superb sensitivity, this survey will be 10 to 100 times deeper than previous generation very wide field surveys after you co-add all the data gathered over the 10 years. So it's going to be wide, fast, and deep. And that's a very impressive thing for a survey to achieve. To sort of show you in terms of an image what the survey will be like, here is an image of just a tiny patch of sky that would be covered by Rubin, okay? And this is an image simulation where people have actually ray traced light through the Rubin optics and worked out what it will look like. And you can see you get huge numbers of objects. And essentially, this is just a tiny patch of sky that Rubin will cover. In total, Rubin will generate 600,000 images like this one, covering, again, the entire southern sky. And these will be time resolved over a 10-year period. And in all those images, by the time the survey is all done, they expect to detect about 20 billion galaxies, about 17 billion stars, and about 6 million solar system objects for which you will actually have measured motions, which show you the orbits of these objects. And all of these will be measured with exquisite photometry. That's the flux of the objects. Image quality, you'll be able to get morphological measurements of the objects in many cases. And then astrometry, measuring to high precision exactly where these things lie on the sky. So that's the overall aim of Rubin. And then I want to now talk about the data side of this, in line with the theme of this talk series. And in fact, this is Rubin's logo. I had this on my first slide, and this logo has a very specific meaning to it. The idea is you're taking light from cosmic sources, a couple of them shown here, and you're then transferring that into digital data for scientific discovery. These are supposed to be the readout nodes on the CCD shown over there. So it's, again, light from cosmic sources, turn it into digital data. So now I'm going to talk about the data side of this thing. The data side is very challenging, and the only way this can be achieved at all is due to the relentless exponential advance of information technology that has been the most powerful force in the world in my lifetime. I was actually born back here in 1970, and today we have computers that are more than 10 million times as powerful as what was available then. And similarly, hard disk sizes have grown very, very rapidly. This is Moore's law being shown here. Hard disk sizes have also grown very rapidly. Sensors have grown very rapidly. That's necessary to make the LSST, the Rubin camera, networking bandwidth, which is necessary to move the data around, and so on. All of these things are fundamentally what makes Rubin possible. And to make that clear, I have here a little table that shows a current assessment from the LSST data management team of their assessment of the data volume. The current assessment is that every night this thing will gather about 20 terabytes of data. And to put that into perspective, that's about watching Netflix for 2 years. That's 2 years of Netflix data at standard definition. And this table here has lots of numbers. But if you look just, for example, at the full output, the output images here, these numbers here are in terabytes, over the 10 years, and the thing builds up more and more and more. So the 20 terabytes comes in relentlessly, night after night after night, okay, for 10 years. And by the time the whole thing is done, you're up at 67 petabytes of data, okay, after 10 years. So and that's just of the imaging data. At that kind of scale, human inspection of all these data becomes totally infeasible. You're going to have to use highly efficient and novel, informatic techniques to actually extract the wisdom, locked inside all these data. Now, how are the data going to flow? Well, they're again taken on this mountain here down in Chile. They then go to La Serena at a base station, and then via actually specifically developed optic cables, they are going to be sent up, some through Brazil, some under the ocean, up to the United States, and then they go out to the data processing facilities. Much of the data is going to be processed at the US data facility, which is going to be at SLAC in California. And then the French and the UK are actually going to help quite a bit with the data release production as well, providing substantial amounts of computation power to make the whole thing work. So the data go from there up to the United States and then are spread out to these data facilities to allow a lot of the very extensive processing work that will be required. And then in terms of, again, the theme of this talk series, I want to say a few words about data, code, and publications. So the processed image and catalog data are going to be provided as openly as possible, okay, to the US, Chilean, and other members of the LSST consortium. And you will often have to ship your code that you want to use to analyze data to the data set. This isn't the type of thing where you download the 67 petabytes down onto your computer and then you start working with it. That just is totally infeasible. You write your code, you ship your code to the data, and then you run on servers next to the data that lets you do that. And that is possible via Jupyter notebooks for people who are familiar with such things. And regarding the data, because all the data are available in a consistent way to all the collaborators in the project, that helps to keep everybody honest. We heard from the speaker last week about the reproducibility crisis that science often has. And, by everybody having access to the same data set, if you publish a scientific result, other people have access to the exact same data and can check if your result is true or not. So that's a very good way of keeping everybody honest, okay? Furthermore, the LSST science pipelines are publicly available for download to a large extent, and much of the code is open source. Not everything, but a lot of it. And furthermore, many of the codes being made by the LSST science collaborations, and I'll say more about them later, is also going to be open source code. So people are trying to be as open as possible with the codes. And furthermore, in terms of publications, and I'll have more to say about them later as well, the astronomical journals have been doing a quite good job in recent years of transitioning to open access. Recently, the American Astronomical Society journals, which are some of the main astronomical journals of the entire world, have become totally open source. So you can get the papers just as well as me. And that seems only fair given that everybody's paying the taxes to allow the work to happen. Furthermore, many of the papers are put even before publication on a publicly available archive preprint server that many people have likely heard of. So those are a few words about data, code, and publications, and I'll say more about those later on. I of course want to say also a few words about people and institutions. This is an enormous enterprise. Many people are working hard to make this thing happen. Here is, a photograph of everybody wearing, except for a few, wearing their official LSST, T-shirts. And this is from the recent project and community meeting in 2022 August. There'll be another one of these coming this summer in August. And this here is a list of the member institutions. I'm sorry that the projector kind of blurs that out a bit, but here is Penn State here. We are one of the official member institutions of this project and have been since about 2005. So here are a few points, in fact, about Penn State. As I said, we've been a member institution since 2005. There are about 10 long-term members in the Department of Astronomy and Astrophysics that have significant research interests with LSST. There is, of course, also further interest in the departments of statistics, which is very important because this is going to be a very statistical enterprise managing and understanding all these data, as well as interest in the Department of Physics. And over the years, Penn State's role has included membership on the LSST Board of Directors, on the Science Advisory Committee, and on the science collaborations. For example, I'm presently serving as co-chair on the science collaboration that will study supermassive black holes in the data set. Okay, so now I want to get on to the science, in fact. So that's my brief overview of Rubin. I want to talk about some science prospects. And Rubin is notable for enabling an enormous range of science with a single large data set. And so I'm going to be giving a very high-level overview here. There's many, many more details that I won't be going into. So there are a few key things that are driving Rubin's design. One of them is solar system studies. The solar system, aside from the planets that we're all familiar with, is filled up with a tremendous amount of debris left over from its formation. That includes asteroids and comets and so on. And by studying that debris, we can learn a great deal about how the solar system formed. And can we fix that? And then I will just say that some of that debris passes from time to time close to, and in fact can collide with the Earth. These are the near-Earth objects. And in fact, what you're seeing here in this background of this slide is a schematic showing the orbits of Mercury, Venus, Earth, and Mars. And then all of these other orbits you're seeing there are orbits of these small objects in the solar system, okay? And the solar system is filled with enormous amounts of this stuff. Thankfully, there's still a lot of space out there, so this doesn't hit the Earth very commonly, but it certainly does hit the Earth from time to time. You probably have heard of the KT event that killed off the dinosaurs, for example, and the Tunguska event. This plot here basically shows the frequency versus the diameter of near-Earth object strikes upon the Earth. Here is an image showing a very large crater up in Canada that happened about 214 million years ago. It's an enormous lake structure now. And the Rubin Observatory will help us identify these potentially hazardous near-Earth objects. And it will do that by observing the sky and then observing a given patch of sky, then going off and doing some other things for a few tens of minutes, and then returning to that same patch of sky. That lets you find, on a timescale of just minutes, objects that move. And then by putting all the data together, you can actually work out orbits of the near-Earth objects. And in total, with Rubin, they are expecting to find about 100,000 near-Earth objects and about 5+ billion main belt asteroids, about 300,000 Jupiter Trojans. Those are asteroids that share the orbit of Jupiter, as well as about 40,000+ trans-Neptunian objects. Those are objects far out in the distant solar system. I want to say a few more words about these near-Earth objects because they're of particular importance. So here, in fact, is an example of one of these near-Earth objects. This one is about 2.5 kilometers in diameter. So if an object like that were to hit the Earth, it would do some very substantial damage. That would be global catastrophe level impact, okay? And this object back in 2004 passed within about 4 lunar distances of the Earth. Okay, so these things do sometimes have fairly close approaches to the Earth. Thankfully, we're pretty sure that we're safe from this one, at least for several hundred years. Beyond that, it's hard to predict in detail. And people are seriously concerned about this. In fact, here is a document coming from the US Congress that has declared that astronomers, in particular NASA, are directed to detect, track, catalog, and characterize the physical characteristics of near-Earth objects equal to or greater than 140 meters in diameter. At that scale, that's enough to produce a gigaton level ground event explosion, bigger than the biggest nuclear bombs. And we've been directed to find all these things, and we were supposed to have done that to a 90% completion threshold by December 20th of 2020. We have not succeeded in that mandate. Of course, as usual with Congress, they're good at giving lots of instructions, and then they don't give the funding necessary to get the work done. But Rubin is an opportunity to actually get some of this done. Rubin will, via the techniques that I just told you, and via this near-Earth object survey, will find of order 75% of these near-Earth objects, making real headway toward, the goal of finding objects that could potentially harm the Earth. So that's one thing Rubin's going to do. Rubin is also then moving a little bit further out, is going to track Milky Way structure. We know that our galaxy, kind of like the solar system, has a lot of debris left over from its formation as well. What this plot here is showing are enormous streams that people have found out in the halo of our galaxy. And these are left over from small galaxies that were gravitationally grabbed by our galaxy, torn apart, and are now incorporated into our galaxy and have left these big streams behind from when they were being torn apart. So Rubin will allow us to find and characterize many new stellar streams, telling us how our galaxy put itself together. It will also let us find many faint satellite galaxies in the local volume of space around our own galaxy. And it will find and characterize and measure the motions of Milky Way stars, many, many millions of Milky Way stars down to faint fluxes. And by studying the compositions of these stars and their motion properties statistically, you actually can pull apart the various components of the galaxy and kind of work out, like an archaeologist, how the galaxy put itself together. So that's another thing Rubin will enable. Moving on then to the changing optical sky. Rubin, as I said, is going to be patrolling the sky with these 15-second snaps. One of the reasons for that approach is you want to be able to find objects that change. And in fact, Rubin's data pipeline, the pipeline that I just mentioned to you, is aiming to deliver announcements of objects that change or move up on the sky within about a minute after they're detected, all done automatically end-to-end with the software. And what this plot shows is a tree of variable objects, including, well, asteroids, which I've already mentioned, and then stars here. And stars can have many fantastic and interesting ways that they vary. You can have eclipses, you can have stellar rotation, you can have eruptions where stars undergo instabilities and erupt. You can have various stellar cataclysms, such as supernovae, when stars blow themselves up entirely. You can have stellar pulsation, and then you can have other behavior, various long-term evolutionary changes of stars, secular behavior. And all these complicated things down here show various examples of these types of stellar variability. And anytime a star, does one of these things, Rubin will rapidly detect it and then announce it publicly to the world, and you will all have access to this data stream just like I will, within about a minute after it's found. And so when people find particularly interesting examples of, say, a new star blowing itself up, you can go chase that down, and everybody in the world can point their telescope at it to investigate that particularly interesting object. And there'll be an enormous stream of these things coming out all the time. I'll say more about that in a little bit. And then this is the one that's particularly close to my heart. Rubin will also advance our understanding of supermassive black holes as active galactic nuclei. So when you have a supermassive black hole in the center of a galaxy, it can eat the gas and the stars present in the center of that galaxy and can thereby produce activity. Okay, and with Rubin, we expect to discover tens of millions of these active galactic nuclei in the Rubin data set, and by combining the Rubin data with other multi-wavelength data sets. And this will let us address a number of very exciting things. It will let us measure supermassive black hole growth in the universe, because these active galactic nuclei represent a supermassive black hole growing. We will be able to measure supermassive black hole growth with truly enormous statistics. We'll be able to measure, for example, how supermassive black holes grow as a function of cosmic environment, ranging from voids to normal environments to the richest galaxy clusters. We'll be able to investigate formation of the first supermassive black holes. Because Rubin observes out into the near infrared, we should be able to detect very early growing supermassive black holes out to a redshift of about 7.5, if you're familiar with the idea of redshift, looking about 95% of the way back to the Big Bang. We will also be able to measure accretion disk structure. So what you're seeing here is a supermassive black hole surrounded by an accretion disk. This is a disk of gas and dust that is being accreted onto the supermassive black hole. And by measuring variability of this accretion disk and also utilizing a technique known as microlensing, we'll be able to measure the detailed structure of the accretion disk. We will also find transient fueling events. You'll notice back on this slide, active galaxies are listed here. Every once in a while, for example, a star will wander in too close to one of these supermassive black holes, will be tidally ripped apart, and we'll detect that, and we'll be able to jump on that. And we also hope to detect examples of binary supermassive black holes, where you have two supermassive black holes gravitationally bound to each other, orbiting around each other. We hope to detect those types of phenomenon as well. So that's supermassive black holes. And yes, and then here, in fact, is some work that's happened here at Penn State, where we are actually getting ready for Rubin. Rubin's going to observe a set of fields even more intensively than usual, called its deep drilling fields. And we have recently used the XMM Newton Observatory to find supermassive black holes in these fields that Rubin's going to observe especially intensively. And in fact, all these little point-like sources here you're seeing in these X-ray images, and these are wide field images. For comparison, that's the size of the moon. All of these X-ray sources are growing supermassive black holes. So we're getting ready for Rubin by laying survey groundwork right now with X-ray observatories and other facilities. And then finally, in terms of the science overview, Rubin is also going to dramatically advance our understanding of dark energy and dark matter, and will help us understand cosmology broadly. You probably have heard that we have come to understand now that the universe has had a complex expansion history. It started off expanding and then was decelerating for a while due to the fact that all the dark matter, predominantly the gravitational effect of the dark matter, slowed the acceleration. But then about 5 billion years ago, so around the time the Earth was forming, for reasons that are poorly understood, a dark energy took over the universe and is driving an accelerated expansion of the universe. And so the universe is much more complex in its expansion history than we had expected a couple of decades ago. Slowing down for a while and then turning around and speeding up. And we want to understand why all that happened. And Rubin will provide enormous data to address that. As I mentioned, Rubin will give us 20 billion galaxies. You'll be able to measure the spatial distribution of those 20 billion galaxies. You'll be able to utilize a technique called weak lensing. And those things tell you about the amount of dark energy and dark matter present in the universe. And then also Rubin will discover, as I will talk about more in a minute, an enormous number of supernovae. And some of these supernovae can be used as cosmic distance measurement tools, essentially as standard candles. And you can then measure the size of the universe using the supernovae and thereby track its expansion history. So that's another great thing that will be enabled by Rubin. So that's an overview. And it's kind of interesting just to think about what Rubin will give us every night. Okay, this plot here, this slide here shows that. So every night we're expecting about 10 million alerts of things that change or move on the sky. This will include about 1,400 or so solar system objects that are observed to move. Those are like the near-Earth objects, the main belt asteroids, the trans-Neptunian objects. And for those, you'll actually measure their orbits. So we'll know not only where are those objects now, we'll know their orbits, we'll be able to predict where they're going to be in the future. We'll also, every night, we'll discover about 1,000 supernovae. That's pretty spectacular. I mean, back when I was an undergraduate student, I remember it was very exciting to discover one supernovae. This thing's going to churn out 1,000 every night. It's just going to be a factory for just dumping these things out. It also will detect every night about 5 orphan gamma ray burst afterglows. These are basically afterglow signals left over when a star collapses down to form a black hole. We'll detect those. Every night it will monitor about 5+ million accreting supermassive black holes. And it will also, every night it will discover about 3 stellar tidal disruptions by supermassive black holes. So as you can see, and again, those are the cases where a star wanders in too close to a supermassive black hole and gets ripped apart. That's what will come every night. And so there'll be more than enough for everybody to work on. It will be completely overwhelming. And in fact, this is where, people have been struggling. How are we going to, manage this? The typical mode of astronomical publishing is you discover something interesting and you write a paper about it. Okay, but that just doesn't work at this scale anymore. And there's been a kind of a joke within the collaboration for many years. And by the way, Google is actually one of the members of the LSST consortium. There's been a joke that we wanted to get the Google people to write a little package like this, where all you do is you type in the paper title and the paper authors, and then you press submit to AppJ and submit to AJ, and the computer does the rest, right? And that was kind of a joke, but just recently, of course, this ChatGPT has come out, and it actually doesn't write too bad text. It's high school level, better than some high schoolers, perhaps. So give it a few more years, and perhaps you could have that thing generate large numbers of papers. I don't know if they would always turn out so sensible or not. But in any case, you have to start to really rethink when you have things coming out at that scale, what astronomical publishing even means. We're going to have to up our game, I think, and move to always very large statistical samples of things and trying to understand phenomena very generally, rather than finding individual things and writing papers about those. I also just want to mention that Rubin, of course, is not going to be out there alone by itself. And this is one of these Gantt charts that shows here the Rubin Observatory, when it will start, and then how long they expect it to be operating, at least for its first 10 years of operation. But while it's operating, other great facilities are going to be coming along. The Euclid Observatory is going to be another very wide field survey, in that case satellite or spacecraft, that will operate in the infrared. The Roman Space Telescope will also operate out in the infrared, another spacecraft. The Square Kilometer Array will be operating out of the radio. Down in terms of gravitational waves, we hope to have many more gravitational wave detectors operating. IceCube will be measuring neutrinos. And so Rubin fits in very well with all these other facilities as well, where if you discover a new gravitational wave source, for example, Rubin, with its enormous field of view, will be very powerful at following it up. And so Rubin plays very well with all of its friends. And in fact, people are now trying to design facilities specifically to complement Rubin and these other things. In fact, we're working very hard right now to put forward a NASA mission called STAR-X, which is partially designed to be an X-ray complement to the Rubin Observatory. So the point here is that Rubin will be operating within a wider context and enables a lot of great science when combined with these other facilities. Okay, now that's all I can say today about the science prospects. There's a tremendous amount more that can be said. If you want to know more, there is the LSST science book, which is publicly available on the web. It's about 600 pages long, good bedtime reading, it'll get you right to bed. In any case, so that can be useful. And then also I will mention that there are a number of science collaborations. These are collaborations of people focused on particular scientific topics, such as transient and variable stars, the dark energy, galaxies, strong lensing, informatics, active galactic nuclei. That's the one I've been most involved in, solar system, and then this is the Milky Way and the local volume. So those are the science collaborations. These all have publicly available web pages, and you can go there to get a lot of additional information about what people are planning to do with the Rubin data being made by the actual people who are getting ready to do the work. Okay, so now I want to end by talking about education prospects and citizen science possibilities. And Rubin has a strong, commitment to education and public outreach. In fact, this is their mission statement. They aim to provide online, data-driven, it's very data-focused, as you would expect for this facility, experiences that are accessible and approachable, adding real-world context and opportunities for people to engage with Rubin Observatory and explore the universe. And in fact, they are just starting to launch their education and public outreach products right now. The full public launch is aimed for February 2023. I saw a preview of some of this at the recent meeting of the American Astronomical Society. They have a bunch of nice YouTube videos. Some of these are already public if you know where to snoop around and find them. This is a nice game for kids where they can actually point Rubin and try to optimize Rubin's observing strategy. And then there are a number of other efforts that are ongoing. Rubin is aiming to provide training for K-12 educators that will help them develop implementation plans where they can actually take a small subset of the Rubin data into their classroom and let students work with that, the actual data, to sort of try to understand and solve some focused astronomical problem. And so they have training opportunities for teachers available. And in fact, we're doing some of that here at Penn State. Every summer here at Penn State, we run in-service workshop in astronomy for high school and middle school teachers. These are the participants from the 2022 workshop, which was on cosmology. Here is the flyer announcement for that one. This summer, we're running one on the lives and deaths of stars. And every year, as Rubin gets closer and closer to operations, I'm folding in and adding in new LSST content and activities, and then trying them out with these teachers, and then they tell me how these things work back in their classrooms. So this is another thing that we're working on. And there are other such programs around the nation, but this is one that's specific to Penn State. And there are a number of other things. Rubin is also aiming to provide, is providing training for graduate students via the Data Science Fellowship Program, where many departments around the nation are not used to training graduate students in this new highly data-focused way of doing astronomy. And so they provide training where graduate students who want to learn this stuff, and there may not be facilities at their particular department to learn it, can go off and learn the data skills needed to effectively work with Rubin data. And then I want to say quite a bit, in fact, about citizen science. So the LSST dataset is a superb source for citizen science projects where people can get involved themselves in working with the data. And the Rubin EPO team is aiming to facilitate citizen science project development by principal investigators. That would be people like me, and I'll say how that will work in a minute, and then promote such projects. And they have some stuff on their webpage here talking about that. The basic idea is the following. The Rubin Observatory, via the management of a principal investigator, will provide its data through the Rubin Science Platform to Zooniverse. And Zooniverse, I will talk about in a minute, is a very effective citizen science platform that already exists out there available for people. And so what Zooniverse is it's the world's most popular platform for people-powered research. More than 1 million volunteers are already associated with Zooniverse from around the world, and they come together to assist professional researchers. And what I'm showing here is a set of example ongoing astronomical projects where volunteers go and look at, for example, images of galaxies and help after a small amount of training, which is provided. You don't need specialized background or expertise. These modules provide the training you need. People go and help to categorize the enormous number of galaxies that are found in these data sets. And that's very important. The human mind does an excellent job at characterizing complex situations that a computer sometimes doesn't do so well at. So there's a galaxy zoo that you can sign up for right now. You can do it today if you want, and start characterizing galaxies. There are also modules on planet hunting, on dark energy, on bursts from space and other variable sources, on studying the aurora, studying the surface of Mars, characterizing all the craters on Mars, making notes on stars, and looking at variable stars. So there's a lot of stuff already going on in Zooniverse, and essentially the Rubin data will just supercharge that And individual investigators who need help, you're going to have 20 billion galaxies. That's enough where each US citizen, if they joined Zooniverse, could have 60 galaxies that could be their own personal galaxies. And they would classify those galaxies and monitor them using the movie aspect of Rubin to look, for example, for supernovae that could go off in those galaxies. And that's how the citizen science will work. It'll be run through Zooniverse via specialized projects where scientists genuinely need help working with this data set, turning it into an understanding. And people, and again, more than 1 billion people have already signed up, will help the scientists actually get the work done. And in some cases, that has led to co-authorship on papers for people who have put in large amounts of effort on Zooniverse work. And then there's also going to be additional opportunities for citizen science. I will say that at least some of the science collaborations that I mentioned are open to non-professionals who are willing to do genuine work. Here, you shouldn't go and sign up if you just want to, get some more emails or something. They're looking for people who are really willing to dedicate significant amount of time to helping the science collaborations move forward. And then furthermore, as I said, Rubin will be finding huge numbers of objects that move or change in the sky, and amateur astronomers, particularly those in the southern hemisphere, can, for the brightest LSST sources, obtain supporting observations, which can be very helpful for monitoring variable objects that otherwise couldn't be studied very well. So that's another way that the citizenry will be able to help science push forward associated with Rubin. Okay, and so what I want to do now is just wrap up, because I suspect I've been gone for a good amount of time now, and I want to just show you here, this is the road to survey start. There's a huge team of people that are working very hard now to make Rubin happen, ranging from the actual building of instrumentation to writing all of the pipeline codes, which are an enormous endeavor, in and of themselves, to doing alert production, to the science collaborations, writing codes that will enable their specific science to be done, through to the education and public outreach and citizen science activities. And here you can see going along from 2018, 2019, 2020, 2021. This is how things are going. This is a fairly up-to-date, Gantt chart showing how things are going. And if things go well, Rubin should be up and going in late 2024, early 2025. That's when they're aiming right now for full operations. It was delayed some by COVID, inevitably, but things are looking promising now. And that's when things will start. So hopefully everybody can get their computers ready for early 2025. And that should be, an exciting opportunity for everyone, professional astronomers and, the general citizenry as well. So that's everything for today. Thank you.